also Anurag Sakharkar from the University of Saskatchewan. If you could all join me in welcoming them to the stage, please.
So I gotta do this animated now, huh? I was gonna be very simple tone and like see how many people fell asleep, but now I'll try to be animated. I'm gonna start saying, well, first of all, thanks to Israel for having us here and all the organizers. And the way the previous panel was ending is a perfect segue to what we're gonna talk about, although it was about international collaboration and how small island nations can work together for space. And this is about bio. There is actually a perfect segue through Victoria's comment, where she said that, hey, maybe you can work together and find consensus of what is it that you could do, for example, a campaign of scientific experiments. And this is a completely and totally shameless pitch, but that's precisely the reason for which I started my company, Jaguar Space, is to give access to space to those who historically haven't had it. May there be scientists or organizations in countries that didn't develop the space station and therefore have limited access to it, or companies who want to commercially monetize, they'll benefit from that. So I thought that was great. And something that is a little tidbit of information. The company was not rolled out. This is a new company. I just have about a dozen customers. NASA is one of them, but I still had not rolled out the make it public until 2 days ago when the announcement of Crossroads in Space came out. So this is, for me, the genesis of the company is forever intertwined with SINC and with the small islands. So now I'm looking forward to working even further together with you. All right, so. Thank you. All right, so space Pharma-Sea. How can we harness space for biomedical research and innovation? And here's what we hope you come out with from this panel. You know how when we have conversations either at work, with non-space folks, or with family, and most of them think like space is a waste of money? A lot of people think that literally the money that goes to, for example, NASA or these organizations or experiments is money that's put in a suitcase on the top of a rocket and flown to space, never to be seen again. Right? So, and usually what we try to convey, no, this is good for you, your life depends on this in different ways, and we say GPS, we say these things, those are all true. But hopefully, after today's panel, you have a lot more ammunition for you to convey the importance of doing this kind of investment in space, and this more specifically on science. We're gonna tell you about drug development and discovery in space with specific facts. We're gonna tell you what kind of research is being done in space, with the note that it's mostly done by developed countries. The benefit that comes from them, financial and otherwise, is mostly being reaped by those countries who invested in doing that kind of research. So please keep in mind that hopefully that's what you get from this panel, and see it through the lens of the small island nations, and that this kind of research really benefits all of us on Earth, and whomever invests in it can also reap the financial benefits of it. All right, with that introduction, I will now introduce our panelists. We have Dr. Roxy Fournier. She's a research associate at the Schlegel UW Research Institute for Aging in Waterloo, Canada. She's a member of the Vascular Aging and Brain Health Lab, which studies space physiology and aging. Her research has covered topics such as bone loss in astronauts, cerebrovascular changes after spaceflight, and orthostatic intolerance after prolonged bed rest. She also currently serves as the Industry Partnerships Committee Chair with the Canadian Space Health Research Network. Please welcome Dr. Fournier.
Thank you, Luis. Okay, so I wanted to start off a little bit more context. So again, Luis, going back to what you said on day one of this conference, actually, that basically everything we know about life forms here on Earth is been in the context of developing in 1G gravity, so the gravitational force that we have on Earth. But now, we actually have had a continuous human presence in space for 24 years now, and a human presence in space since 1961. So we've learned a whole lot of stuff about how a whole lot of organisms develop in microgravity. Not only microgravity, but partial gravity. We have centrifuges on the ISS now. But let's not forget the incredible facility that we have, the ISS and Tiangong Station now. These fantastic research facilities and what they've been able to do for our understanding of how life develops under different gravitational forces. Why should we care about this? That's the big question. That's what Luis was trying to start off the panel with is the why, the how, and all these things. So I will give a little bit more context about my research and why it might be important for life on Earth. So there's a bunch of different things we do in Canada, in my lab in particular, that are relevant for people on Earth. So you might be wondering, okay, why is this person working at the Research Institute for Aging? Sounds like I have nothing to do with space. But you may have heard that space is sort of like accelerated aging. And it's pretty true. We see it in a lot of different organ systems. We're really interested in vascular and cardiovascular health in astronauts. So if you can imagine yourself floating in space up there, you are no longer under the gravitational force. The bones that your body has built up for until you become an adult now, you've got these fully formed bones. What happens to them in space? Well, basically they get completely resorbed by your body. This is a natural process. But this happens as we age as well, right? Osteoporosis. Huge issue across the globe. It's not just developing nations. Across the world, osteoporosis research, there's still a lot of unknowns in this field. And as we have kind of transitioning to having a much greater population of folks who are now 55 and older, we need to be able to take care of these older folks who may be at greater risk of osteoporosis, but also cardiovascular disease. So we're finding really interesting things about what happens to astronauts' blood vessels, for example. So you have things like stiffening of arteries, and this also happens to people who start to develop increased blood pressure as they age. And so what we're looking at specifically with really cool techniques in space is what's going on at the walls of these vessels. What's going on with the cells? How are they responding to microgravity? What role do they have to play in the development of this disease? And we can take that information back to Earth and be able to come up with novel ways to treat the stiffening of arteries, which causes high blood pressure, cardiovascular disease, still pretty much the #1 killer across the globe. So we study that. I studied a lot of bone loss in my PhD in astronauts. And one sort of interesting story that I like to tell, and actually Anu, you mentioned this as well, is the cool story of Amgen working with NASA. This is a biotech company that develops drugs. And they were working with NASA to look at how mice lose bone in space. They send these mice up into space, and then they can actually treat them with these new drugs that they're developing and see whether or not these drugs are effective for this really rapid bone loss. Like, it's bad in astronauts, but it's even worse in mice because their lifespan is so shortened that even spending like 2 weeks in space, they lose a dramatic amount of bone mass. So they studied this new target that specifically targets a type of cell called the osteoblast. So this is involved in osteoporosis. And they had some really interesting results. So we can actually build on this space research now, and that drug is actually currently being used on Earth. So that's just kind of another the way that space can benefit drug research, finding novel targets, treating these diseases that are really, really prevalent on Earth. So with that, I think Anu has a little bit more insight into some other pathways, so I'll let Luis introduce him.
Thank you, Roxy. All right, now I'm going to introduce Anurag Sakharkar. He graduated from the University of Saskatchewan in Canada. He is also a space biologist and research associate at the Lukong Lab, studying specific genome-wide responses to spaceflight to identify countermeasures for negative effects astronauts face while in space. Anu has also worked as a space biologist at URI, a prestigious space biotech and space access startup currently headquartered in Germany, developing Earth biotech applications for spaceflight research. Anu has won various national and international awards for his research and is notably the youngest person ever to be named a World Emerging Space Leader by the International Astronautical Federation for his contributions to astronaut health research and prominence in the field at his young age. Please welcome Anu.
Thank you, everyone. Thank you for the kind introduction, Luis, and thank you to Ms. Rose for inviting me to be a part of this panel. I just wanted to build up on what Roxy talked about with bone health. I think bone health is probably one of the most prominent and one of the most important aspects of space physiology that are really disrupted. And Luis can also definitely talk about this more with all of his like experience on ISS experiments and stuff. I believe NASA focuses mostly on bone health for astronaut health, but I think it's also important to keep in mind that literally every single system that we've looked at is affected in microgravity. It's not just bones. Muscles is one of the most important, I guess one of the other most important systems that are affected. Astronauts, I think, lose I've seen some studies say as high as 1% of bone and muscle mass per month, which is really, really significant because the oldest 5% of the population loses 1% per year. So that's really another aspect of space biomedical research is you can apply the drugs and the gene targets that you find from applications like this, from applications like the astronaut health on the space station to older populations and kind of looking at how these drugs and how these targets can really be used to treat bone and muscle loss in the older population. Something else that we've also looked at is, in my research, we focus on, instead of trying to find individual genes that are important for astronaut health, we focus more on genome-wide responses to astronaut health and characterizing how the genome as a whole, which is a collection of all of your genes, responds to spaceflight and the stressors that you experience in space, as opposed to just individual genes and how those genes react. And something really interesting that we've seen is those stressors and those genome-wide responses are not seen anywhere else on Earth, right? Which means that spaceflight is a completely unique stressor to Earth organisms that have literally evolved for 4.5 billion years in 1G gravity with normal convection, with like no hypoxia and like none of these issues that you face in space. So I think spaceflight is definitely a very, very interesting avenue for biomedical research and biomedical advancements on Earth. Something else, I guess, that I think is important to note is that astronaut health is not a solved problem, right? Astronauts work out for, I think it's 3 hours every single day?
It's a bit less than that.
Okay, but I can't imagine they're too happy about that. And yeah, it's really disruptive. And they're still losing 1% of bone and muscle mass per month, right? And that's not sustainable long term. And that's part of the reason why I think the longest experiments we've had are like 1 year, but most of them average around like 4 to 6 months, I think, or even shorter.
Most missions, yeah. On the ISS, about 6 months.
Yeah, and that's partly because of all the health concerns that astronauts have, like staying out there so long and losing that much bone and muscle mass. And if you see like videos of astronauts coming back and doing like the press conferences right after they exit the like shuttle landing, you can see that they're like about to faint and they're being held up by like 4 or 5 people. So yeah, I think astronaut health is not a solved problem, and really investing in astronaut health can pay huge dividends for Earth health in general.
Perfect, thank you, Adam. And in fact, my mom has osteoporosis. My mom uses this drug called Prolia. And not only that hits home when you know somebody who is taking advantage of something that took place in space, but just think about these two statistics. Amgen, the company who did this, this was a couple of payloads that were flown in space shuttle by NASA Ames, Amgen, and Bioserve, where I used to be. And Amgen right now is selling over $4 billion a year of this drug. And they have a 12% year-to-year increase in sales. So now that's, as I said the first day to folks on SCAC, that's not only doing good on Earth, it's doing good on Earth in a financially sustainable way, right? Now it's a company, they're making a lot of money, that's a whole different conversation, but the point is that this is a very tangible output of doing space-based research. It's not that space was a magic wand and boom, it is. Now the drug is developed. But this molecule is just going through the FDA process, which is the US government needs to make sure this is going to be safe for people to use. The fact that it did that in space because it's an accelerated model, disease model, was key to that part. So I'll say that, those two statistics to keep in mind. And 30, 40 years from now, people are gonna, our children and grandchildren are gonna think like we were like completely like so barbaric the way we currently take medicines. So if somebody here has the same disease as I do, we take the same doses, the same number of days, that's gonna be so strange in 34 years. We're like, really? That's how you did it? That makes absolutely no sense because every human body is different. And that's what we're moving towards. It's called personalized medicine. And that we're starting to do, and we have done it in space as well. So there's these two experiments out of Stanford that I was managing. They were called Cardinal Heart. and we flew tiny little hearts, basically. So these were cells, they were cardiomyocytes, endothelial cells, and fibroblasts. First, they were tissue. It was like 1 centimeter in length that we had in 2 pillars, and you could see them beat. And this is just calcium channels. This is not that it's alive and part of a living and feeling organism. These are just cells sending an electric signal from one cell to the next. In the second experiment, we actually flew spheroids. So these are small, tiny. It was like, imagine a penny, a U.S. penny in size, and in that area we had 96 spheroids of tiny little hearts. But here's the thing: what was being done in that experiment is taking advantage of microgravity, because microgravity acts on those tiny little hearts in the same way as when you're aging on Earth, or you have some cardiac muscle atrophies, some diseases. So what we were doing is, for each of these different little wells that had 96 spheroids, they represented different demographics of the US. So we had African Americans, we had Caucasians, they had Hispanic, and the molecule was being tested to determine how does that ethnicity, that background, impact the effectiveness of the drug that we were testing, and then that should inform how those doses of medications should be taken differently based on your demographic background. Now, right now we're just moving towards those types of backgrounds, but the intent is that eventually it's going to be more personalized. So, as you think about, for example, small island nations, it's a very different ethnicity. What is the background as well? But nobody's studying that, for example, right? So this is where we start looking into, okay, we can start getting more personalized in these medical kinds of research. So I think we just gave a few examples here of how it's currently being done and how it can benefit people on Earth. So we have a couple of questions, but really the intent is to make this as engaging as possible. So what we're gonna do is we're gonna do one round of questions, and then we're gonna start asking you questions about what we said to see who's paying attention. All right, I'm gonna start with Roxy. Oh, and this is a fireside chat, or as I like to call it, side fire chat. So it's like more back and forth questions, but again, the intent is that it's more engaging, and this is an opportunity for you to grasp information that you can later convey of, hey, that's why, one more reason for which space matters, and science in space matters. All right, Roxy, what is the capital of El Salvador? That's wrong. So why do some organisms thrive in microgravity?
Yeah, okay, so we just told you for the past, I don't know how many minutes, that cells and organisms respond terribly to microgravity, and they can inform disease. But there have also been cases where cells actually have shown to be kind of happy in space. They actually develop better than they would on Earth. And one example of that is cancer. So what happens on Earth when you start to have a tumor, and what happens after that makes it really bad? It's when it starts to metastasize. So if you have this tumor and then it kind of branches off into your bloodstream and goes and finds another organ to target, that's a huge problem. Now, in space, this happens a lot easier. We've actually taken these cancer cells to space, plated them on sort of like a two-dimensional surface like we typically do on Earth. And what researchers have found is that these cancer cells, they love to just separate and then just float off and do their own thing. And it's a really good model of metastasis. And so there's a lot of things that you can do when you have this model in space to better understand what's happening on Earth as well. There's a huge correlation between the two, right? So for a cell biologist like myself, the things that you would do to better understand metastasis in space would be, okay, well, what are the factors that are making it so easy for these cells to just lift off and just form these floating spheroids and go attach to other things? It would be, for example, things like sticky proteins on their surface that are better expressed. And so those sticky proteins can then help them, I don't know, find another target. So that's just like one example of something that a researcher could find, like, wow, look, this protein is much higher in concentration, or this gene is much better expressed in these particular cells, and that could possibly tell us a lot more about the process of metastasis. Like, so in cell biology, there's actually a lot that we do not understand still to this day about how cells behave. And so space is a really, really good environment to look at how their behavior is changing, what kind of structural differences these cells are undergoing, what kind of genetic changes are happening to these cells. We can do all of this type of research. We can even start doing it on the ISS. It's really cool. We have techniques where we can run PCR and look at changes in situ. We don't even have to bring the cells back on Earth. So yeah, cancer cells, huge benefits for humankind, and space is bringing that technology, it's advancing that technology.
Perfect, thank you. Anu, what's the most recent precedent you can think of for spaceflight being used to help pharmaceutical research on Earth?
I would say I think the best example I could give for like pharma research in spaceflight would be Keytruda. So Keytruda is a cancer drug. It's a monoclonal antibody, so it's a biological drug that was synthesized by, I think, Merck & Co., which is a big pharma company. And what they did was, for safety testing, it's obviously easier to give a drug intramuscularly. So imagine EpiPens, right? EpiPens are so easy that they hand them out to people with severe allergies, and they essentially, all the instruction you need is basically just stick it in your thigh, right? And so it's easier to administer drugs intramuscularly as opposed to starting like an IV or something, which requires a medical professional, like a nurse or a doctor or someone to actually do that for patients. So Merck developed this drug called Keytruda for various different types of cancers, and what they did was they wanted to get it certified for intramuscular or subcutaneous, which is under the skin administration. But the crystals that they had of the drug to get it certified, they weren't like clean enough. So what Merck did was they sent up the drug to space, and they crystallized the drug in space. And because spaceflight has such unique physics in that there's no convection, there's no there's nothing to really disrupt the crystallization process. The crystals that Merck was able to produce were a lot cleaner, and you can actually see images of the crystals, and it's like such a unique, like just a completely clean crystalline structure, which you never ever see in pharma research on Earth. And what they could do with that clean crystalline structure is actually get their drug approved for subcutaneous administration, which probably saves them billions and billions of dollars. And it's a pharma company, so probably not most of the profits weren't transferred to the consumer, but I'm sure some of the savings were. And so I think that's a really unique way to apply pharma research on Earth, or pharma research in space to Earth applications, is like actually just certifying drugs in space for better for better administration.
Yeah, no, that's right. And the benefit to people is that instead of, if for folks who have these types of cancer, instead of sitting for hours to get the IV and frequently, now it's a shot. And basically the way the whole protein crystallization thing works is if a protein finds another protein of the same type, and they match. So they start building what we call crystals. And in space, they do so slowly. There's no flow making them move from one place to the other, so we can grow very large crystals in space with respect to Earth. And why does that matter? Because once you have the crystal, you can take images of it, crystallography, there's different approaches, but if you understand the structure of the protein, then if it's the protein that is causing the disease, now you can design another molecule that is going to go bind to it, to attach to it. It's like two Lego pieces. You need to make sure they have the right shape. Or if you're building a molecule to treat a disease, you need to understand what is the right structure. This is the example of Keytruda. By Merck flying this to space, they were able to grow these crystals, but here's the key part. They don't need to fly this to space every time. They just did it the one time, and now with understanding the protein structure, they can repeat the process, they can change the process on Earth for the synthesis of this drug, and with that they decrease the viscosity, they decrease other properties of the drug, which made it possible for folks who have these diseases to get a shot in the doctor.
All right, now a question for you, Luis.
All right, fire chat.
Side fire chat. So tell us an aha moment that you've had in one of your spaceflight projects that you've been involved with.
Okay, I think that's easy. That involves her. This is Peggy Whitson, NASA astronaut. I've had the fortune of working with a lot of astronauts, and I am a super fan of two who are just ninjas for science in space. Is Kate Rubins and Peggy Whitson. They're just superstars. So I look up to them as scientists. Peggy Whitson did the spaceflight part of one of the cancer experiments I worked on. I worked on lung, prostate, and breast cancer experiments in space. And what she was doing in space, I was in the payload operation control center taking notes of at what time did she do what are the temperatures, and as soon as she was done, I would run to my lab and do the same things for ground, for the Earth. So in this experiment, this was lung cancer, I have the cancer cells under the microscope, and I can see the cells. They look like tiny little like bubble tea. They look like spheres that you can see through. And I had them on focus on the microscope, and as soon as I went a little bit up or a little bit down on the microscope, changing the focus, everything would be out of focus. Meaning that this was flat, like a disc. It's just one layer of cells, at most two. And that happens because on Earth, we got the gravity, and it's kind of like trying to build a tower with bowling balls. When you make a first layer with balls, and then you try to put the second one, its own weight will make it collapse. So we have this bidimensional structures. So I take the images, I introduced the drug we were testing, which by the way, the startup for which we were doing this got acquired. That's another promising avenue of another drug that had a space aspect to it. But as I see this, and then I'm seeing what Peggy Whitson was showing us from our microscope that we had on space station, and she's seeing the cancer cells, and it's like the beginning of Star Trek, just traveling through the stars. It's just this ginormous three-dimensional structure that was built in microgravity that we couldn't build on the ground. And that matters because then when you have molecules that you're testing to see if they can actually kill the cells that are in the core of a tumor, then you have the right morphology, you have the right shape. And if you don't, you can have false negatives or false positives of a molecule that you're testing. And it could have been a cure, but because you have the wrong shape, you get data saying, oh, actually this doesn't work that well, or the other way around, a false positive saying, hey, this worked really well, but in reality, in vivo, in the human body, it will not work because the way it permeates through cells will not work to get to the ones in the core. So just the difference that day when I could see with my own eyes how flat the cancer cluster of cells I had in my lab versus what Peggy had in space, that was just mind-blowing. I was like, I want to do this again. More research. All right, I think with that, we're gonna open it to Q&A, and wonder if there's any questions from the audience at this point. Because if there are not, I'm gonna start asking you questions of what has been said.
I was gonna ask a question, actually. Thank you. One of the things I was wondering is about how do you train astronauts? Because as we can see, they need to be trained doing more and more things because more and more requirements are coming from science. Like I need you to print this chicken nugget, or I need you to like work with analyzing drugs. So are you finding any challenges training the astronauts? Because there are also a few of them able to go up to space. Thank you.
Do you want me to take that? Okay, so right now the way it's done, they get training for a specific experiment. So usually if you're recruited for a space mission, you're given like this long list of experiments. So typically, I don't know, maybe like a dozen experiments that you'll be in charge of for that mission. And training starts 6 months basically before you actually launch. What you learn in those training sessions, you don't remember a thing once you're in space. So there are processes at NASA that make sure that the astronaut knows what they're doing. They get a lot of support. Look at NASA alone is just like this massive entity of thousands and thousands of people. A lot of those people, their job is to make sure that these astronauts know what they're doing once they're in space. So even though they may have forgotten their training pre-flight, the day prior to, let's say, an experiment, if they know what they're going to do the next day, so they know that the day prior they have to prepare. So just like for any exam, for a student on Earth, you have to read all the documentation, make sure you know exactly the steps. They provide them with very, very detailed protocols, like really detailed protocols. And then the day of, we can sometimes actually walk them through it as they're doing it. So for example, in my lab in Canada, we're the only lab in Canada that has a direct link to the ISS. And so we can actually watch them on a screen on a TV. They can't see us, we can see them. We can talk to them. And we ask them to run biomedical experiments. So we ask them to do ultrasound on themselves. So they're holding an ultrasound probe on their neck. And we can actually tell them, oh, you're a little bit too far to the left, to the right, whatever. Okay, can you move it here? And then they find the spot and we tell them, okay, the next thing you're gonna do is hold it in place and like walk them through the steps. So even though they may not have a background in like medicine or life science. I mean, oftentimes the astronauts that get recruited in our studies have no background in this at all. And they're totally fine doing it. They're superstars. So usually, just based on the fact that these are superhuman people who just can retain information really well, it certainly helps, but we have all these mechanisms in place to make sure that they know what they're doing.
That's right. And something nuts is that you usually train them 6 to 9 months before they launch. So, and they get trained in a bunch of experiments. So what I've noticed is that, like, again, pitching here, Peggy and Kate, what I've noticed is that by the day of the experiment needs to be performed, they already know it, and usually it's because the night before, on their personal time, they read these crew procedures, where we have these steps that Roxy was saying that is very specific, and then the next morning we're ready to start, and they know what they're doing, and she's telling us, okay, now I'm gonna do this other thing, right? So it is pretty impressive that, you can tell why space agencies selected them. They're pretty good at it. Thanks for the question. Other questions? Awesome. Here in front.
So bone density loss and muscle atrophy in space, that's an accelerated process. So when you're treating osteoporosis in people who skew older on Earth, what kind of differences do you see in how they're being affected by these drugs?
Okay, well on Earth, you have the benefit of being able to do, what's that word, like a therapy that includes physical therapy, right? In space, you can't have the inclusion of, like go and walk 5 kilometers per day to help you build that bone density back up. If you have osteoporosis on Earth, let's say you're bedridden, you underwent a really complex surgery and you had to be in bed for 3 weeks, you've lost a bunch of bone mass. Usually you're given this protocol afterwards to rehabilitate, and that involves physical therapy. In space, you can imagine that doesn't happen, so typically, they do have a treadmill, they use it, it's not as efficient, it's not as effective as us being in Earth gravity and having that weight applied in a very specific way on our bodies. So it's an open question still. It's actually a very good question that you ask, is does the bone get built up the same way as someone who's on Earth? These are still open questions. We would have to look at the microstructure of the bone to determine that. And it's definitely a very, very interesting question that a lot of bone scientists are currently asking.
I think I read a paper like a few years ago on lacooning, like not being present in astronaut bones after they come back. So to give you guys some context, bone is kind of a weird way the cells are structured in bone. The bone matrix itself is not alive, right? And these bone cells are basically in little, they're called lacunae because they look like lakes. So they're like little divots in the bone, and then the cell sits inside the divot with like tendrils extending out for blood supply and stuff like that. And apparently in that study, they looked at astronaut bones that were like reformed after coming back to Earth, and they noticed that the bones were missing lacunae, which means that either the cells were like sitting on top of the bone, like just sliding around, or like something else weird was happening where like the bone structure was being created and then like the cells were dying out or something. It's really an unanswered question. And I think that's very important to keep in mind, is that repair for astronauts might not be the same as repair for Earth. And so we need to make sure that when we look at astronaut health, we keep that in mind.
I got one anecdote. It's not statistical analysis, but my mom, she fell about 2 months ago. She was in the market in Guatemala, and she's like going to get her veggies here and there, and some person didn't look, and he emptied a box of whatever product he was putting in the shelf, and threw the box when my mom was walking, and she's in her high 70s. She tried to dodge it, she couldn't, and she fell, and I remember her telling me, I thought that was it, because at that age, usually you have like a pelvis, feature or something. It tends to worse things because now they're bedridden, and like there's a bunch of other things that happen. And she tells me, I thought that was it. That was the beginning of the end. And she was perfectly fine. She had a bruise on her hands and her knees, and she tells me, like, this has to be that drug like that I'm taking, which is this Prolia that I was telling you from Amgen. So that's one anecdote, not statistical analysis, but I think for me it brings home that it is working. It's my mom, so I care a lot. You got another one?
believe you don't care about normal patients, Luis.
Try to contextualize it. The new thing I learned in this panel is the EpiPen element. So as someone who is having some allergies now in my old age, we do not have EpiPens in Maldives. We don't. Is there a mechanism to build a competency? Like, what does it even mean to be creating, like, what sort of infrastructure facilities is required to make EpiPens at that? Like what's required for those sort of things, right? But then conceptually, grounding it down to the gaps that exist. Like no EpiPens in islands, no EpiPens in the city, but like talent, right? How to echo, like, is there remote medicine, remote sensing sort of stuff that's like, how do astronauts or the ISS, how do people do sensing? Like, are they all doctors? Like, what are there any overlaps? Like, are there anything that we can bring from those learnings to these remote dynamics? Yeah.
I can speak to that a little bit. There's a couple of PIs in my university actually working on like miniaturized sensing, and Roxy's smiling because she's working with one of them, I think, or at least she knows him. And yeah, I think remote applications for medicine is one of the big things that are going to come out of space health research. Because astronauts kind of have to rely on themselves, and as we go to the moon and to Mars, like you have to remember that when you're on the other side of the moon, you can't talk to Earth, right? Because there's a big moon in the way, and it's like whatever many kilometers of rock in between you and whatever signal you're receiving from Earth. So if something happens on the other side of the moon, you're in the dark, right? If something happens at Mars, you're like 8 or 7 light minutes away from Earth, and so like you're by yourself. And like a heart attack can kill a person in 8 minutes. So you have to really be cautious of that. And I think NASA and like all the other space agencies, they are working on, and they have worked on creating telemedicine and like remote health aspects of healthcare on the space station. But it's something that we really need to work on. So I don't think astronauts are really self-sufficient at all when it comes to medical emergencies and stuff like that. Of course, they do receive some training, and both of these people can talk a lot more about that than I can. But yeah, medical training is definitely needed, and we need more remote health monitoring for sure.
You want to add anything, or should we?
There's a lot. I could talk for hours about this. So Canada is really interested in this topic. We are investing a lot in miniaturized technology. So Anu alluded to this, but we're developing a miniaturized MRI. So think about hospitals and how much infrastructure an MRI machine takes up: space, money, power.
Helium.
Helium?
Yeah.
Okay, yeah, helium. So a lot of resources. So imagine a world where in the Maldives you could have the equivalent of a hospital inside a tiny clinic. That is what the Canadian Space Agency is planning to do. We're currently building at the headquarters a demonstration site where we're inviting companies who have novel technology that can be applied to space to put into this tiny box. It's probably the size of a shipping container or something like that. And they want to make everything nice and IoT integrated, like everything's talking to each other. A very layperson could use all of it because it's going to have like an AI assistant and like all of these things. And that's what we're going to take to the moon. So all of these things can absolutely be used in places like the Maldives, where every island is basically on its own. And the idea is that we want an island to be self-sufficient like that.
And for context, for those who are not that familiar with population distribution in Canada, most of the population in Canada live close to the border, the south border of the states, but there's a lot of pockets that are isolated. And I don't know if Roxy or I don't know who, a Canadian recently said that's why it correlates with island nations. We have these isolated communities that are very uncommunicated with where the rest of the folks are.
And also we have like a lot of snow and ice and like a really bad weather for like 8-9 months of the year, and so like it's really difficult to get medicine and like resources to isolated pockets of population, and so we really need telemedicine and we really need self-sustaining medicinal infrastructure, which is why Canada is investing so much in remote healthcare, and that has real applications for the space station as well.
Yeah, we're even talking about doing drone delivery of biosamples or drone delivery of medications and things like this to places that are, within reach of a drone. But like Louis said, we have like very remote communities living in Canada. And so this would be one particular way that maybe technology can access these folks who cannot get, like physically cannot get to a hospital or a clinic that can give them care.
Perfect. I think Emma had a question.
Hi there, thank you very much. I mean, I found this all mind-blowing, obviously, the idea that we're gonna personalize medicine and now with science fiction and tomorrow might be real, it's fantastic. I was just wondering if at the moment we're still speaking about ground-based research related only to academic environments, or we are already seeing small startups or companies that are actually investing in some project, and if you can name some of them, who do you think is already ahead of the race when it comes to commercialization of these ideas?
Commercialization of doing Earth, the Earth part, or doing, okay.
There's a lot of startups. We have this one particular, what is it? It's kind of like an incubator in Canada called MedTech. And they had a specific sort of, I think it was called Orbit Health. So they were inviting companies in Canada who have technologies for Earth, but can also be applied to space to be part of this sort of incubator program and help them move them along in their technology development. A lot of these concepts are actually TRL 5 and 6, like they're advanced. And it's worth mentioning too that a lot of technologies that are being developed for Earth, like these miniaturized MRIs and all that stuff, their purpose is, they didn't start a company thinking, oh, I'm gonna be a space health company. There's no market. Literally, your only customer is gonna be space agencies, right?
Eight people, yes, that's it.
Right now. But these companies are positioning themselves to eventually serve the commercial LEO and lunar Mars infrastructure. This is a long way away. Right now, they are totally focused on serving communities that need it most on Earth. So, for example, in Canada, we have like these remote communities. I can't speak to other countries. This is what I know in Canada, but I assume it's similar in the United States and maybe all spacefaring nations, right?
Yeah, there's a good example. It's called Lambda Vision. They're based in Connecticut, and what they're doing is they're actually manufacturing retina implants in space. And the retina is this part in the back of our eye that it has these proteins, and these proteins are almost cylindrical in shape, and they're oriented in parallel one to the next. And basically, these are the ones that are responsible for receiving light and then transforming it to electrical signals that go to the nerve. And as we grow older, there's a degradation in their ability to perform their function, and it is hard to make good implants on Earth because it's very hard to keep these proteins parallel. And not only that, you want to make this layer by layer in a fashion that you maintain this parallelicity of these proteins in different layers. On Earth, it's very hard because you have convective flows and they start like doing all these things, and then when you put it in a human, that signal is not that well, so they see blurry. Now, Lambda Vision, what they're doing is they're actually manufacturing them in space. Now, they can do the first layer, proteins go parallel, then when that is fixed, they go for the next layer, and so on. And now this is something, and this is one of the things that I'm doing with my company, is techno-economic analysis to determine when does it make financial sense to do something in space. And this is a very good example because what they're bringing back to Earth is very tiny. It's oval in shape, and then when it comes back to Earth, they cut it in the right shape. But the mass and the volume of what they're bringing back to Earth is very tiny, so they have to pay very little to do so. And the value is high because then that even though although the process is complex to do it in space, what they can do is better and sell it at an equivalent price than the competition on Earth. So Lambda Vision is one example. For cancer, Oncolinks and N3D Biosciences are some of the startups that we supported to do cancer research in space and that have since been acquired. So I know that one of the CEOs of one of those two companies, he exited, he got acquired, and then he went to start another company, and he also acquired, now he's an angel investor.
And when it comes to academics and industry in biotech, I think there's a lot more industry, but that's just like the case for normal biotech anyway, right? Because once you find an important gene, there's lots of money to be made, right? Like drugs are made multiple tens of billions of dollars on the regular, and that's very common. So once, like, even in academic labs, once labs find drugs, that's 4 letters that's worth 20, 30 billion dollars at minimum, right? And so you always have spin-offs, even on Earth biotech, without even including space. So that's why I think we see a lot more industry in biotech when it comes to, as compared to academics.
Perfect, thanks. Oh, more questions, cool, there's engagement, I like it, thank you.
So first of all, thank you, for this interesting presentation from your side, but also debating with the audience. I would like to add in this particular point, there is a market, there is no market. Let's say that we are living in a beautiful time because we are in transition from a centralized economy in space where the agency were committing to the industry to develop something for their own purposes. Now they are moving to commercialization, free market, so means that the company needs to raise their mission video and they look for customer. Of course, because we had this previous regime, let's say the market is not educated to buy a product made in space. That's it. That's why we don't find the big pharma shopping in space sector, because they think it's not a market for them. Now, we are in transition. There are many startups that they are moving on, and also the agency are drastically changing their way of operating. So for instance, in Europe, we have the European Space Agency has a program that is called the Scale Up Invest, that if you are selected, the agency is giving you up to 80% of the price you make for your customer. So you have a customer, you present the project to the agency is scaling you the risk, and I can tell you that the company being selected, they already solved this opportunity because it's a good tool to create reliability in space and to make the customer paying, not having for free. And on the other side, we have a big bottleneck that has been a fantastic experience in the ISS, but was not done for doing in-space production. There is too much turbulence, the quality of microgravity is not uniform, and when you produce, you need that. And then you need to produce a consistent volume of optical lens, protein crystallization, whatever, that you would like to monitorize one launch up to space for a million on Earth. New platforms are coming up. There are space planes, there are capsules that they can come ad hoc for your customer request down to Earth. So sometimes you do something on the station and you have to put everything frozen until you have a way back. So I think there is a lot to convey this ecosystem in a way that we need to converge the need and to consider space as a normal laboratory, even closer than 400 kilometers. That's it. Thank you.
Absolutely, great point. Thank you. I think the analogy of what's happening right now with so many companies building space stations and all this, and for context, my previous job, I was a senior business development manager for a company in the States valued in $5 billion, building their own fleet of spacecraft and space station. Basically, what I see this as is when the internet was put up originally, or when companies started popping up in the late 90s on the internet. So the US government set up the investment of setting up the infrastructure, the internet, and then companies or people started doing their own little business on it. Or when I see, for example, Las Vegas in the United States, the government put the streets, the water, the electricity, and then people could go buy lots and start their businesses. We are in a similar situation right now with space, where all these companies are investing their own money to go build that infrastructure of spacecraft, space stations, etc. And there's an opportunity for countries that haven't been engaged with space to be engaged with space without having to build their own rocket fleets and their own space station. But now is take advantage of these commercial opportunities, and I think that's an important message for island nations and countries all around the world who haven't been engaged in space.
Yeah, there are experiments, there are products that you can make for pretty cheap. Now, let's say even on small like CubeSats. There are a lot of student groups even that are able to study different cell types or create different organoids in a very small space. There are companies like Anu, you worked for Yuri, like they developed these cool little capsules that have automated systems to look at different types of cells or different types of tissues and things like that. So you can do this very cheaply. That could definitely be an opportunity for an emerging space nation to get into the space health field.
Yeah, and I think bio research is quite expensive in and of itself, like even on Earth. Companies with price cap on Earth. So when you move into space, it's not as huge of a jump. It is still a massive jump, but I don't think it's as huge of a jump as compared to maybe other types of research.
Perfect, and we're almost out of time, so I wonder if you want to do any closing remarks, or you feel like these were the closing remarks and we have time for one more question?
Let's hear more from the audience.
Okay, let's do one final question then. I think here in front is the first one.
Hi, I'm actually a radiographer and my name is Nagu. My question is regarding the bone mass. Is there like a difference between the weight-bearing bones and the non-weight-bearing bones, and is there like if there is the recovery also the same, or is there a difference between that?
I love this question, thank you. There is differences between weight-bearing and non-weight-bearing bones. We've studied, these days we do a lot of looking at the ankle part of the bone and then the wrist here as would be your example of a non-weight-bearing bone, and this would be like a weight-bearing bone. There are some interesting differences. So astronauts use their arms a lot to maneuver on the space station. And yet, you would think like, oh, maybe the radius, the arm bone would not degrade as much, but they still do lose a lot of bone mass. So we're seeing on a microstructural level, trabeculae are lost, even in the radius. What I find super fascinating is they did studies of mice, and they looked at the cranium, which has a completely different structure, completely different cell organization in it. And what they found was, so Anu was talking a little bit earlier about a specific type of bone cell called the osteocyte. And this is a very important component of weight bearing because they sense forces every time you take a step on Earth. These cells are triggered, and they make sure to keep your bones nice and healthy. But in the cranium, those don't really, there's no weight bearing there. The osteocytes are kind of not even there to some extent. In mice, there aren't really that many osteocytes. And they found like opposing responses in microgravity between the osteocytes in the cranium bones versus the weight-bearing bones. And that could be an effect of the fluid shift towards the head. And so you're getting like an increased intracranial pressure, and those osteocytes may then be like actually more stimulated in space than they would be on Earth. So a lot of differences, still a lot of unknowns, and we don't know if this happens in human skulls because you can't really just do a CT scan on someone's head for no reason. So yeah, we've looked at mouse studies. There's still a lot that we could learn. So yeah, thanks for the question.
And we're out of time, so just finishing with a fun fact. The reason for which we get our blood pressure measured always in the arm is because the blood pressure changes as a function of height. At the bottom there's higher pressure, it's hydrostatic pressure. So Roxy was mentioning about the fluid shift in space. This fluids go up in our body, same thing inside the head, and these fluids come back up. So the astronauts tend to feel like when we're all stuffed with a cold. So they cannot really smell that well or taste that well, and that's one of the reasons for which Tabasco is so popular in astronauts. They put a lot of spice so that they can actually feel some flavor in the food. So random facts, so hopefully now you've learned a few things that you can convey with family over dinner of why space is awesome and it's worth investing in it, not only for GPS and other technologies that we've talked about, but for drug discovery, things that benefit people on Earth. And you also learned that Tabasco is very popular in space. So thank you to the panelists, and thank you for your attention.
Panelists, thank you. That was a fantastic presentation.